photoelectric effect was discovered in 1887 by Heinrich Hertz. If you remember, Heinrich Hertz was the one who discovered electromagnetic waves, following the predictions of Maxwell. Now, what Hertz found was the following: that an electric spark would jump across a gap more readily when the room lights were on than when the room lights were off, that is, in a darkened room. The spark would jump across a gap more easily with the lights shining on the metal electrodes. Well, a year later, it was Haworks in 1888, and I've written his name here on the board, was Heinrich Hertz. Haworks discovered that the light had to shine on the negative electrode of a spark gap. If you used a plus and minus potential, that the light had to shine on the negative. Shining on the positive electrode didn't make any difference. 10 years later, it was Thomson who showed that the negative charge on any electrode gradually leaks off or disappears when light shines on that electrode. And the same year, Lenard, a German, Thomson was English, Lenard was a German, found the same effect independently, that any object, any metal surface, charged negatively would lose its charge if light shines on that surface. Now, I'm going to show this photoelectric effect in a very elementary way. I have here an optical bench again. Here is an arc lamp as a source of light. And here in front of it is a lens. Now, this particular lens is not a glass lens. It's made of quartz, because I want to have in my beam of light not only visible light, but infrared and ultraviolet, particularly ultraviolet light as well. Now, glass, ordinary glass, absorbs most ultraviolet light. And so by using a quartz lens, then I can produce here a beam of light, visible, ultraviolet, and infrared. And this beam of light is going to shine on a piece of metal here that is zinc. Zinc is the 30th element in the periodic table. And this metal is mounted on an electrometer. And I'm going to charge that zinc plate and the electrometer negatively with this rubber rod. I'll put the charge on until it's clear to the top. A full charge. Now I'm going to turn on the arc lamp, and you watch the needle of the electrometer. You can see the light shining on the zinc metal surface. And the needle falls. And rather rapidly, too. Now I'm going to charge it again, and I'm going to put in the path of the light a piece of glass. I'll hold this glass in the path of the light, see if I can get a full charge on the zinc metal. Well, that's fairly well charged now. Now I'll remove the glass, and you watch the needle of the electrometer. See it go down. I'll put the glass in and stop it from discharging. The needle, if it would stop oscillating a little bit, would stop somewhere around 12 the scale. Now I'll remove the glass and watch the electrometer needle go down again. So it is that the glass seems to stop the discharging of the electrometer. Now, ordinary window glass like this does not transmit ultraviolet light. This piece of glass is just as opaque to ultraviolet light as a piece of metal or a piece of black paper. But it does transmit all of the visible light. And so we can see from this kind of an experiment that only ultraviolet will cause this emission or leaking off of negative charge from this metal surface. If one charges this zinc with a positive charge, shines ultraviolet light on it, or visible light, or both, it will not show an discharge at the electroscope. It must be negatively charged. Well, now what happens is, of course, is the ultraviolet light comes in, hits the surface, and kicks off these electrons. And these electrons are called photoelectrons. They're no different from any other electrons. They're called photoelectrons only to distinguish the way in which they are liberated from the metal surface. Now, the photoelectric effect, as you've seen it demonstrated here, has many practical uses. But since we've seen here that ultraviolet light shows the phenomenon or kicks off electrons, how can we produce the same phenomenon with visible light? Well, it's found that most of the elements and most metals electrons, photoelectrons, only with ultraviolet light. There are a few, however, and those are largely the alkali metals that emit electrons when visible light shines on such a surface. Now, the alkali metals, you remember, are lithium, sodium, potassium, rubidium, and cesium. And these elements are particularly useful in photoelectric cells, or in the magic eye, as is more popularly called. Now, here on the board, I have diagrammed a very common variety of photoelectric cell. It looks like a vacuum tube, a glass envelope, and inside a metal cylinder, a half of a metal cylinder really, connected to the outside, and along the center, the axis of that cylinder, a wire that is a collector. Now, what one does is to charge this cylinder negatively and this collector in the center positively. And hence they obtain the names cathode and anode. The cylinder becomes a cathode. The collector in the wire is called the anode. Here's a top view of a photoelectric cell. Here's the half-cylinder metal plate looking down on the top. It's the cathode. And since it's to emit electrons by light, it's called a photocathode. Charged negatively by means of a battery. Shown here, the negative side of a battery. The positive side connected to the wire in the center, the anode. And in the circuit, one can place any kind of a device, a milliammeter to show current flows when light shines in, or one could put in here an amplifier and amplify the current. Now, when light shines in to such a cell and strikes the surface, electrons are knocked off, photoelectrons are emitted, we say, and they're drawn to this anode, this positively charged electrode. And so one has an electron current flowing across here, and hence a current flowing around the circuit from the negative side of the battery across here and around. In a darkened room with no light shining on this cell, no current will flow. So the photoelectric cell, you see, is like a switch that is turned on when the light shines on the photocathode, and is turned off, or open circuit, when there's no light shining on it. Now I'd like to show such a photoelectric cell and one or two practical applications, or at least how these practical applications can be brought about. Now here's one of these little photoelectric cells, standard commercial type, every one of you can buy in the store. You can see the little semicircular plate, I hope, with a little wire rod up and down through the center. That's the anode. And while the base of the tube has 4 prongs, only 2 of them are connected. Only 2 of the little prongs at the bottom are connected. One to the anode and one to the photocathode. By turning it here, you may be able to see the cylinder better. Light reflections are rather bad. Now, such a photocell here on a board, same kind of a cell, and it's connected to this switch to 4 dry cells that are under the table, and in series with the 2, just as on the blackboard, is this milliammeter. And when I put the switch on, you watch the milliammeter show a flow of current. Because the room lights are fairly bright, and they produce a current here. Now I'm going to put my hand over the photocell to cut out most of the light, and you see the milliammeter shows no current, practically none. Take my hand off, the current goes up. I'm covering the light, now removing it. Covering the light, removing. Covering, removing. So you see one obtains a fairly large current. Well, not very large, this is a milliammeter, but a current when the light is allowed to shine on the photocathode. And this photocathode is made sensitive to visible light. Now, you see, since a current flows, when light shines on it, one can send that tiny, tiny current through an amplifier and make it stronger, or a 2 or 3 stage amplifier. Make the current stronger and make it operate, say, an electric relay, a little switch that closes and opens. And then that switch that closes and opens can be made to operate anything. You can open your garage door or open the door in front of the store. There are thousands of applications of such photoelectric cells as this. Well, here is a commercial type of board that one can buy with a photoelectric cell on it and a little dial resistance. This particular one has a buzzer on it and a little light bulb. Just to demonstrate that with light shining on this photoelectric cell or not, one can operate a relay, electric relay that will turn on or off any kind of a device you wish. And I'll just show this with a buzzer here. I'd better turn it on first. This little switch here will enable me to use this buzzer in this photoelectric cell. I'll see if I can get a current strong enough to make this little buzzer go. Now when I hold this lamp, you see the buzzer doesn't go. I'm shutting off the light. But now if I let light in, with the room lights on, it's rather difficult to keep all of the light out of the cell. I'm trying to cover it as well as I can. But the minute a little bit of light gets in, it turns the buzzer on and off. Now one can, in a darkened room, make this turn on the buzzer with the light when the light comes on or when the light goes off, either one. So one can make such a device do anything you want it to by the interruption of a beam. If you have a beam of light shining from here, from a flashlight into here, you can have it so that when somebody walks or a car goes between two beams, the relay will maybe start a counter moving, count the number of people or the number of cars that pass by a given point. Photoelectric cells have thousands of applications. Most of them make use of the interruption of a beam of light to make them operate, to make them do things. Now I'm going to show a practical application of the photoelectric cell. I'm going to send sound waves, sound vibrations, so to speak, or music over a beam of light. Now this is done by, and of course use the photoelectric cell to change the light back into sound. I'm first going to show you on the board a diagram of the apparatus I'm going to use, and then we'll see the demonstration. I have a little transmitter consisting of a small box on which is mounted a little neon glow lamp, very small neon glow lamp of a common variety. And this neon glow lamp is connected to a little amplifier that is inside this box. And this box is going to be connected to an ordinary record player. And we're going to turn on the record player, and instead of producing sound as you do it normally in a record player, we're going to have the varying current from the vibrating needle and the pickup. We're going to have it vary the intensity of the glow from this neon lamp, so that the lamp source of light gets faint and bright, bright and faint, very rapidly or slowly, depending upon the music vibrations of the sound producing the current, so that the light intensity will rise and fall exactly in the same way that the sound waves rise and fall in amplitude and frequency. Now what that does is to take the light that comes out from the neon glow lamp and give you then a beam of light from this lens that is rising and falling in intensity. This lens is so arranged that this source is at the focal point. And that produces then a beam of light that can travel across the room or can travel several miles, as a matter of fact, to a distant point, a receiver, where another lens here brings the light to focus on a photoelectric cell. And here's our photoelectric cell that will change light into electric currents. When the light is bright, we'll have a large current, a large number of photoelectrons here. When the light is faint, we'll have a few photoelectrons. And so the rising and falling intensity of this beam will be reproduced in electric currents by means of the photoelectric cell. Then those tiny currents are amplified by a 2 or 3 stage amplifier and put into a loudspeaker. And so we'll be able to hear the music played by the record player in the receiver. Now here is our little turntable, which I can turn on when we want it turned on. And the wire connection comes from the changer or player over to this little plug input on this little amplifier. Now right here is our little neon glow lamp, and it's now just come on and is glowing with a steady light. But when I start the record player going, the light intensity here will rise and fall. You may have difficulty seeing the little glow lamp, the color of it, but it's now lit. It's an orange color. Now the light from this little source comes out here through this lens and becomes a parallel beam. And this beam of light travels across the tabletop here to another lens. And here this beam of parallel light then comes to focus on this photoelectric cell. Now this photoelectric cell has to be covered over to keep out as much as possible the room lights. Because the room lights rise and fall in intensity a little, 120 times a second. The alternating current causes room lights to fluctuate intensity, and the photoelectric cell will pick up that 120 cycle hum, we call it, or 60 cycle hum, and produce a loud roar. So I'm going to put over this photoelectric cell this little tin can that has an opening on one side to let the light come in. And then a cover, a cardboard cover, to keep the light, most of the light from the room, from entering. The light now will enter the lens, go through the little opening in this tin can to the photoelectric cell, I hope. Now I'll turn this on, and this turns on a little amplifier here with 2 stages of amplification, and then puts it into this loudspeaker. Now we'll turn on the record player and see if everything is operating. Now the sound you were hearing was coming from the little speaker over there, and the light and the sound was actually being transmitted as light over this beam of light. And to show that it's traveling by a beam of light, I'm going to interrupt the beam when I turn it on next time, interrupt it at different points with my hand, and you listen. Interrupted over here by the source just as well, as long as one interrupts the beam of light. Voice transmitted over, or I should say music here, transmitted over a light beam. The actual sound vibrations were not traveling from here, from the transmitter to the receiver. It was light. But the light fluctuated intensity just as the sound waves fluctuate. Now, you perhaps have never realized it, but this very same process, almost the identical process, goes on every time you watch a motion picture. Because there the sound has been reproduced by means of a photoelectric cell, and the music, the voice, has been transmitted over a beam of light. And here's a simple diagram of a moving picture film projector. Here is the spool of film that's is fed through the projector. It travels, as most of you know, through what is called the picture gate here, where light comes through the film and is focused on a distant screen. But here, the film, I point out, as most of you know, it goes through here by jerks, by jumps. A picture stops here, light goes through, a shutter comes across here, cutting out the light. The film jumps to the next picture. The shutter opens up. Light comes through the next picture and onto the screen. Shutter comes across. The film jumps to the next picture. And so through here, 24 pictures per second. Find this film going through intermittently by jumps. Now the sound is produced by a little so-called soundtrack on the side of the film, and to produce proper sound, the film must go at a steady rate, smoothly and steadily. And so the film is brought over a sprocket wheel that turns at a constant rate, passed over another one that turns at a constant rate, so that the film can move through the sound gate here at a very steady speed, steadily. And there, light passing through the soundtrack causes the light intensity to rise and fall as the voice vibrations that produce the sound in the first place. And then, of course, this is the take-up reel for taking up the film. The sound that is being reproduced here corresponds to the pictures that are passing by here. And there's a standard distance between the sound and the pictures that are being projected to put the two in step. Now, I've reproduced on the board a small section of a film to show where this sound track, as it's called, is located. And this is a small sketch of a piece of film that's used today in the standard projectors, where 4 sound tracks are used, magnetic tracks are used for stereophonic sound, and 1 optical track is used in theaters where they're not equipped for stereophonic sound. Here on the side of the film are two of the sound tracks, and here are 2 other ones. These are magnetic. We're interested today in the optical sound track that uses the photoelectric cell. Well, the optical sound track runs along here, close to the perforations on one side. And then, of course, here are just 3 sections of pictures along the film. Now I'd like to show you in animation these sound tracks. There are several different kinds, how they're made, and then how they're used to reproduce the sound from a moving picture film. So let's take a look at this animation diagram of film production. Here you see a piece of film with the soundtrack on the left, little lines, horizontal lines, dark and light, along the left-hand side, and the arrow points to a picture and now to the soundtrack. You see the soundtrack has little black horizontal lines. Now this little white line is a beam of light that falls on the film when the film is being made, and the sound vibrations make this little beam of light vary in length, and you see trace out what is called a unilateral variable area soundtrack. Now, if both ends of the little beam of light are made to fluctuate according to sound vibrations, it will trace out this kind of a black and white pattern soundtrack, and this is called a bilateral variable area soundtrack. Now, if the width of the little beam of light, the horizontal width stays constant, but its thickness varies, then one obtains what is called a variable density soundtrack. A variable density soundtrack. And here are all 3 shown, close-up details of the 3. Variable density, bilateral, and unilateral variable area tracks. Now here's a method by which the variable density track is produced. You see little jaws of a slitter vibrating up and down with the voice vibrations, varying the intensity of light that gets through them to the screen or to the film where they're being recorded. You see these little slits, little jaw slits, are made to vibrate by the currents that come from the original voice. Now here, original voice is shown entering a microphone as sound waves, producing variable electric currents that go through an amplifier through these little vibrating slit jaws that produce the variable area, variable density soundtrack. Now here, the sound is being put back, the soundtrack is being put back into sound by the light that passes through the soundtrack onto a photoelectric cell. The lower center is the photoelectric cell. Here are 2 animated diagrams of photoelectric cells, one receiving a variable density, one receiving a variable area soundtrack. The light coming through falls on the photoelectric cell, and because of its varying intensity, the sound can be changed, or the varying light intensity, I should say, can be changed back into varying electric currents. And in the loudspeaker, those change back into sound again. Well, that is sound reproduction as you see it in the motion picture theater. Sound, so to speak, on a beam of light. Now, We're interested not only in practical applications, but in the theory that lies behind the photoelectric effect. It was Einstein in 1905 that first gave the correct explanation of the photoelectric effect. He said that light waves, when they fall on the surface, have an amount of energy equal to a constant h times the frequency of the light, h nu. And this is a very important concept. Every light wave, called a photon, has in it an amount of energy given by this constant, a universal constant, has one and one value only, times the frequency of the light. The higher the frequency of the light, the greater the energy. A light wave comes in, says Einstein, and the energy of that light wave is transformed. Part of it is used in getting electrons away from the surface, and what is left over goes into kinetic energy of the electron. And Einstein wrote down this equation called the photoelectric equation. It's a conservation of energy. H nu is the energy of the light wave coming up to the surface. W is the amount of that energy used to pull the electron away from the surface, and what is left over gives it kinetic energy. So you have available H nu in the form of energy. Part of it gets the electron away, and the metal wants to hold on to its electrons. That's why it had it in the first place. And whatever is left over gives it kinetic energy, gives it velocity, if you please. This is called the photoelectric equation. It is a very important equation. Incidentally, it was on this equation, for the writing down of this equation, that Einstein was awarded the Nobel Prize. Look carefully at what the constants mean. H is called Planck's constant. It was a constant first proposed by Planck. Nu is the light frequency. W is called the work function. The work function. M is the electron mass, and V is the electron velocity. The Einstein photoelectric equation. Now, the early attempts to measure H, Planck's constant, A.L. Hughes, O.W. Richardson, and K.T. Compton all independently tried to measure H and were reasonably successful. In 1912, this work by these three people. For several years after that, Millikan worked very hard trying to determine accurately Planck's constant, H. And it was for the evaluation of H, the accurate evaluation of H in this equation, that Millikan was awarded the Nobel Prize a few years later. The value of H, generally accepted value today, is the following: 6.62 times 10 to the minus 34th joules times seconds. If you multiply joules times seconds times the frequency, you get joules, which is a form of energy. Now, there are one or two effects that I should speak of, we're going to make use of later, that are associated with the photoelectric effect. I don't want you to confuse this, however, with the photoelectric effect. If you have a metal surface here, and an electron comes down and hits the surface, it may knock off 2 or 3 or 4 additional electrons. This is called secondary electron emission. Secondary electrons. These are secondary electrons. This is a primary electron, and the process here is called secondary electron emission. Now, such a principle is made use of in what is called a photomultiplier tube. And here's a diagram of a photomultiplier tube, and we'll discuss these later in connection with counters. But in the top of such a tube is a photocathode. Light comes in and emits a few electrons. These electrons are accelerated toward another metal, where each one will kick off 2 or 3 by secondary electron emission. Those electrons are attracted toward another plate and kick off a few more. And so it is, by having plates here, down here, one can amplify, so to speak, the number of electrons by using more and more of these secondary electron emission plates. And this is called a photomultiplier. It's a photoelectric cell, really, but it amplifies the current instead of by means of vacuum tubes, by means of secondary electron emission. So we've seen today the photoelectric effect and photoelectrons.